All right. Good afternoon, everyone. Welcome to the PACTRANS Regional Transportation Seminar. As you know, we invite outstanding scholars come to talk to our PACTRANS students and researchers, our partners, collaborators, each quarter. And this PACTRANS seminar will also be broadcasted over the internet. So today, I'm honored to introduce our PACTRANS Autumn Quarter Seminar speaker, Professor Xiaopeng Li. And Xiaopeng Li is currently the Harvey Spangler Professor in the Department of Civil and Environmental Engineering, and also the Electrical and the Computer Engineering at the University of Wisconsin-Madison. That's another UW. He served as the Executive Director of Smart Highway Research Center at University of Wisconsin. He founded the Connected and the Automated Transportation Systems Lab, which developed a multi-scale connected automated vehicle testbed. Previously, he directed the US DOT National University Transportation Center. He is a recipient of the National Science Foundation Career Award and has led over $35 million funding in federal, state, and industry-funded projects, plus $25 million in match funds, mostly as the PI. He has published over 140 journal articles, holds a PE license in Wisconsin, is an ASC fellow, and an IEEE senior member. His research interest includes autonomous vehicles, evaluation, connected vehicles, sensing with spatial intelligence, and transportation systems analysis. Maybe you heard about Waymo is going to test the autonomous vehicle in Seattle area, and how do we ensure the autonomous cars are safe, right? Dr. Li's research is directly trying to answer such questions and how we could evaluate the safety using our academic research simulators and other relevant tools, right? So now let's welcome Professor Xiaopeng Li to start the seminar.
Thank you, Dr. Wang, and thank PACTRANS for actually setting up this great event. I'm very pleased and honored to be here, and I thank all of you for being here, especially those who have obligations, and thank you for dropping by despite your tight schedule. So today I'm going to think about to address the safety of autonomous vehicles by looking to the behaviors of autonomous vehicles as well as the human-driven vehicles which are surrounding autonomous vehicles in real world. So yeah. Okay, so it works. So as Professor Wang mentioned, Waymo has already been tested. In the lunch, I saw a professor showed a clip of video of Waymo's been tested. But I think many of you know that Waymo has been deployed their autonomous vehicles in several cities and try to expand. And so when we talk about autonomous vehicles, that first thing that comes to our thought might be Waymo or something similar. But in fact, actually, there are a lot more other technologies that are also automated vehicles that are probably have more impact to our traffic systems and has more implications to traffic performance. I call them production automated vehicles. These are the vehicles that you have automated vehicle features, and you can buy in your private cars. So, for example, many production vehicles have already level 1, level 2 automations. Over 90% of the vehicles, new models have that kind of automation. And plus, like Tesla already has L2+, which is kind of like similar to Waymo. I actually have a Tesla 14 at my car. You can click a button that will take you out from garage and or your driveway and get to your destination and park there. of course, you have to be responsible for their driving. So it's not level 3, it's level 2 plus. And also a lot of other automakers internationally have a similar mindset. So you're going to see this kind of automated technologies are transiting from a single function automation to more of like a supervised or unsupervised full automation. And that will have a lot of the new behaviors and driving patterns. And these vehicles are, their market penetration rate increases very fast. And we have 200 plus new vehicles models per year with this kind of like automation functions, and also AV software updates a lot. So they have a lot of different configurations. Then there is a strong need for measuring their performance on safety as well as mobility and energy, because they're really already been deployed and already impacting the traffic. So the fundamental problem, let's think about it. Let me mute it just to avoid that. So is actually, you think about these autonomous vehicles. When the vehicle model hardware is fixed, and you give it a version of software, you know, its behavior is fixed. It's already like that. And let's say if you put it in a fixed driving environment, let's say city of Seattle, and then its performance should be determined, right? It's already there. It's just like you don't know, and how to find it out actually is a center problem, fundamental problem of evaluating autonomous vehicles. How do we find them out? One way to find them out is to look into the crash records. Like some states like California has separate records for automated vehicle-related crashes. But it takes years to get collected the record, and also, you know, you need to suffer from a lot of crashes and even deaths to find them out. And also the information is quite limited and aggregated. Then, you know, of course, companies have a great amount of data, and they release some data, but you know, in a way, they're kind of like selective. Like Tesla reports their safety, like if you look at these curves, it's much better than actually average human drivers, you know, like 80% improvement in terms of crash rate. But there are other reports saying that they have like highest fatality rates. You know, like the same car, but if you just select the report from different angles, we're going to see, you know, the beauty side and the ugly side. So, or, you know, there are, I think the most impactful way of, you know, spreading the autonomous vehicles impact is actually the influencers and media. And you probably see a lot of videos like this. I tried to make, I don't know, Tesla as, like, I don't know, motel, hotel. Like, they have actually, if you know that, it has 20 million subscribers, actually. You know, then they would think that autonomous vehicle would be like that. And also there will be some dramatic tests that going on, you know, like to put it to autonomous mode and let it crash on something, you know, that's pretty eye-catching. But do they answer the fundamental question? Maybe not. They're designed to attract attentions, actually. They're going to set up particular tests. Oh, you know, like, and it has very high cost to do this, and a high risk if you keep doing this. And also the outcomes are just like ad hoc results without the scientific rigors or statistical significance. And so now let's see, as a scientific community, we have tools to really do some predictive measuring. Like when you think about predictive measuring, maybe simulation comes to our thought. Traffic simulation like this, kind of like a VSUM-based simulation, you have a lot of other simulators, are widely applied to predict the mobility energy impact. And some newer simulators, you know, like Tesla, and this is a closed but open source ones like Cosmos, you know, they can do really high fidelity simulations. But the issue is that their safety outputs are not calibrated against the real world behaviors. They can, you know, like a traffic simulator is usually collision free, it doesn't have any collision. So if everything runs like simulation, then we've reached the vision zero. And this kind of simulation looks like fancy, but their behaviors are like, you know, just are not calibrated. You never know its performance. So, and at this point, I think we're in a good time as public universities to think about, to fill this role. There is a gap about how to scientifically evaluate the performance, actually, as public institute. So, you know, there are so many things that we need to do. You know, like data, AV data, human-driven vehicle, VRU data, road geometry, all these things. We still need a lot of those data, and I mean, companies have data, but they don't share it. We need to measure and share across the community. And we also need to really understand the behaviors based on the data, like all kinds of behaviors, AV, HVs, and finally put that into some kind of like evaluation environment. Could be simulation, could be real world, or could be like hardware in a loop. And we need to think about to do some accelerated tests, and finally get performance measured and rank them like US News or something. Actually, I meant to talk about this later, but I just to give you a heads up. We're actually calling for an open source activity. If you have any development, you can. We're going to set up a platform, and hopefully you can link your development to this platform if you see any relevant. This is not just my thing. It's actually collaboration across multiple institutions that are working on different pieces of this. And yeah, sure. So we can talk more about it. So our lab has done some work in these areas. So today we're going to mainly talk about the behavior part, and I'm going to give you a heads up about the accelerated test as well. So I'm going to talk about the core problem about AV and HV behavior model, and that is very important. If you don't formulate them very well, you're not going to have any collisions in simulation, or you're not going to be able to analyze the safety in a predicted way. So let's see what's the fundamental gap here. Let's look into the simulation structure or modeling structure. It's basically following a Markov-Chain paradigm. All right, you can think about if you have an autonomous vehicle or an HV. The first time you bring it out from a factory and put it to the road, all right, you can have a snapshot. And then next second you have, or next time step you have another shot. You're going to have a shot again and again until it either crashes or it burns its life, right? It's get demolished or something. So you can actually characterize them as each step is a state, and some of the states are just like free flow. Some of the states you interact with vehicles more closely, and the behavior governs how you're going to transit from one state to another, like Markov-Chain, right? You can see, this is just one realization, and you can have many realizations of the life of an ego vehicle, and you do the union of all these states, you're going to get the entire collection of the scenarios you can look into. And for each state, you can have an adversity measure. That could be TTC, it could be crash severity, or you can come up with something that can be related to the significance of the safety measure. All right, and I use different colors to represent that from safe to severe crash. And also each state may have different probability. Like free flow, you may have a higher probability, but this kind of a, crash scenario, near crash scenario may not have as high probability. So if you overlap them together, you can use this kind of colored hexagons to represent all these states. I mean, let's say in the ideal world, if we can enumerate all these states, we can actually plot them over a Markov-Chain graph. Sorted by the adversity measure, from safe all the way to critical crash, this is a really crash, and a severe crash. All right, you're going to find a lot of high probability scenarios are in the safe side, and this is going to get down rapidly. And then there's a little bit of scenario states that happen during a crash. I mean, assuming that if you have this, then it's like a lot of problems can be addressed. All right, so the life cycle is going to be like a sample chain. You start from here and go to the next step, and then jump to the next step, and all the way to a crash, or actually end of its life. All right, and then you know all the dynamics. And what's the use of this graph? Okay, it can tell you a lot. So the error size of these states is actually crash rate. The distribution of them tells you the severity of crash. And this part may be near-miss distributions. And this part could be traffic oscillation that links you to like a traffic flow theory, all right? And some kind of stop or go traffic. This part is stationary traffic, fundamental diagram, all these things. All right, so it looks like you can address that traditionally separated topics in transportation, safety, mobility, energy, all of them together within this snapshot. So it looks like if you get it, it's like that's the end of transportation engineering, right? Just joking. And the center of it is actually you're going to learn this behavior. So what characterizes a Markov-Chain is actually state transition probability from a current state to the next state. All right, it may have different possibility going to different states. All right, so as long as you can characterize that, you know all these behaviors, you can predict these distribution patterns, you can solve all these problems. All right, so this is the core of the simulation. This governs the behaviors of each agent in this kind of simulation, and also based on the previous analysis, it's going to give you the all performance measures if you can get it well. But then what happened in the real world is, okay, we have a lot of measures here, but we don't have many measures here, or we almost have no measure. I mean, high fidelity measures, you can do the behavior level analysis. So right now, the current simulation and modeling are actually, you're going to using part of the observations to predict that's quite stretchy. And existing behavior models represent, you can use them to, that explains why mobility and energy is fairly well studied, because you can observe them, right? But, when you want to extrapolate to safety behaviors, all right, it's possible that you can get some kind of distribution that feeds the data very well at the beginning, but really is quite off during the tail. Actually, if the tail much underestimates the distribution, then that explains why our current simulation doesn't have crashes, they're collision free. So we want to fill this research gap by looking to whether there's certain behavior patterns that's going to enable you to extrapolate this behavior with limited observations or no observations here, but you can still get the patterns that represent like realistic crash behaviors. All right, so this is actually the gap we want to fill from this study. All right, let's look into some of the model, actually. The problem statement is like, let's think about a simple problem, all right? Just one dimension. There's one road, traffic goes this way. You look into two cars, and this is the ego car, and you get a snapshot of every step, and you can use X to represent the state. This vehicle's location speed and the gap, or this vehicle's location speed. And then that you're going to have input from the history window to the current time point. All right, what is your output? Based on that, if you're doing simulation or traffic flow theory, you'll be able to predict where the next step is. And one step further, you can predict that. We're going to leave this to be solved by an AI model. All right, AI will capture some kind. But what really matters is not just these two. It's actually distribution pattern of this. I would say acceleration deviation, for example. What's the deviation from the mean? I'm going to use delta. Is a sigma tilde to represent it. All right. So the devil is in the details or tails, actually. Like these two tails. All right. So the distribution pattern really matters a lot. Whether you're going to have this kind of distribution or that kind of distribution is not just a matter of the standard deviation and the mean. It's actually its own distribution pattern. So how to look into this? Again, the first step we're done, get the key parameters, and then we're going to look into the distribution of the acceleration deviation. It's of course mean is 0 because it's a deviation from the mean. Standard deviation is like, or variance is calculated based on this prediction. You can normalize it by dividing it by the standard distribution, and we found that if you do this, and then the time is not sensitive, you can actually make this kind of normalize the acceleration deviation into a distribution with 0 mean with 1 standard deviation. So the question narrows down to what kind of deviation pattern we can fit to this. All right, maybe we see some studies in the literature using normal distribution. All right, you can see the normal distribution is like it has the parameter, the delta. The sigma part. This is acceleration deviation is in the exponent All right, so that decreases exponentially. And you can prove that from the theory saying that, okay, the probability for you to exceed a certain level decreases exponentially. And then if you do that like measures of this kind of deviation, these are normal range and these are tails, you're going to see it drops a lot. But then we looked into the real data. Actually, it goes like this. There is quite a lot of discrepancy in this area. And the tail distribution of normal distribution or classic studies actually really don't matter. They really don't match this. And then the problem is whether we can come up with a new distribution that matches this pattern. Actually, we found out actually we can easily find one new distribution that only has two parameters that can fit the data fairly well. All right, it comes in this format. I mean, instead of sigma, the variables being an exponent, they're now in polynomial terms, so they're power law. It's not intuitive, but actually, if you do the manipulations, you're going to see, this sigma bar is actually standard. It's like normalized acceleration distribution. It has a relationship with delta, which is defined as a violation rate. It's actually, if sigma is here, the delta is the shaded area size of these two parts. That is a probability of going beyond the sigma bar in this distribution. All right, it's a simple power law with a parameter k and a. All right, let's see how well it works. So we need to have data. All right, that's just theory. How do we get data? Of course, we collect our own data, but that's far from enough. Okay, we actually get data like Waymo, Argoverse. These are high-level vehicles, but we also have a lot of other, production automated vehicles, and we also have human-driven vehicles in different geometries that got them from 3 continents, various geometries, diverse AV brands. All right, and we did the test. We found that, all right, that power law actually describes all these data fairly well. This is a human-driven vehicle data from multiple locations about longitudinal behavior, maybe car following. This is actually lateral behavior about lane changes. All right, you see, this violation rate is, so this scaling law is a straight line, and the empirical data is actually the dashed curve. You see, in all these instances, they match very well, even if in the tail part. I mean, we haven't gone to the crash error. We don't have crash, but some of them are near misses here. So it looks like with 2 parameters, you can catch this trend very well. If you have more data, I can test if this scaling law can further gather. But with the amount of data we have, it looks pretty well. And also for autonomous vehicles, it works very, very well as well. Just 2 parameters, actually. They work fairly well. Then, now see, okay, why you're going to use this kind of shifted power law, not other distribution. If you use Gaussian distribution, do a fitting, or if you're looking to the probability density, plug them into the log scale. All right, this part is fairly well, but when you get to the safety critical areas, they're like several orders magnitudes off. Actually, that's why we much underestimate the crash probabilities in the critical areas for H3 longitudinal, H3 lateral, and AV. All right, so that's actually reveals a problem. All right, and you can make this model even simpler by fixing A and just leaving K there. All right, one parameter you can fit them with, I don't know, an average of a 0.97 R² value. That's a pretty good fitting, actually. All right, that way you only have a K parameter, average 0.94. That's pretty good, actually. And this AV is fitting still very good from different places. But so this is actually really exciting. You find out a simple rule with 1 or 2 parameters, and here's 1. You can fit, you calibrate them. You fit the different HV and AV data very well. Not only in this like safer region, but also in the near-miss regions. All right, that's pretty surprising. Then we actually look into the distribution of different Ks. A smaller K value may represent more unpredictable driving behavior, and we look into their predictability. And there is one point that is a little bit separate. This is actually our lab vehicle. We programmed it, fix the driving pattern. So that's why it doesn't have lots of deviation. But others maybe have more uncertainties. All right. But what's most important is whether this works for simulation. All right. So we do nothing, we just put it into the simulation, let it run extensively. All right, maybe we spend like a couple of months to run them actually. We still have pretty fancy computer with GPU and distributed computation, but we still spend a couple months to run them for like, I don't know, over is like close to 50 million miles, I think even more actually. You're going to see, if you're just using the classic model, Gaussian distribution, after driving this many miles, you're not going to get any collision for both stuff, AV and HV. Right, that's collision free. Even if you feed real world data, all right, still collision free. But if you use our model, we didn't do any fine tuning against the crash. We didn't do collaboration. We didn't do any calibration. We only calibrated with the non-crash data. Look, the crash rate it gives is like 3.1 to the 10 to the negative 6 for HV, and 1.3 10 to the negative 6 for HV. And if you look, we don't know the exact values, but we know some of the statistics. They are at the right order of magnitude. Actually, just, I mean, they're not going to exactly match because there is no real world data about this. But if you look at some, you know, the order of magnitude matters. These match very well, just the 10 to the power 6. This is only 1.5 times bigger than this, maybe due to the geometry or other settings, you can easily find that. But the most important thing is like, these are off like 0 and these are just like, match each other very well. And also the pattern looks like match. HV is still more dangerous than AV behavior when they're activated, which is consistent with some of the report findings. That means AV is still going to be helpful. And also we look into longitudinal rear end area collisions versus lateral cutting collisions. Their percentage is quite consistent with the real world findings. So yeah, that means, okay, it gives us the promise that you will be able to potentially combine the traditionally separate areas, traffic flow analysis simulation, and safety, like post-crash bits. Safety is, you know, if you're a safety person, you know, you mostly like to use the statistics, look into the post-crash sense. But pre-crash analysis, you can do this extrapolation and you can combine them together. Actually, that's very exciting findings. Okay, so for more information, go look into this archive paper. And so now I want to talk a bit more. Once we have AV and HV behaviors, all right, how are we going to use it? Of course, it itself doesn't tell us. You have to do like evaluation. You need to test many scenarios and put that into a simulator or field test, and then run them extensively and get the performance metrics. All right. So, you know, we're not the first to work on this kind of accelerated assessment. I have to put lots of homage to our colleague, Professor Henry Liu at UMich, and he's done a lot of fantastic work. So I'll tell you what has been done in this area, and you know, like they have developed accelerated evaluation method. So the baseline is Monte Carlo simulation. It's not acceleration, but you can understand it based on this Markov-Chain graph ranked by adversity. So basically, you're going to do a sample pass here, and let's say not all the way to the collision, but just m steps. All right, m is still a big number, starting from a nominal state like free flow or something, and then you run m steps. That's a sample pass. You can do k sample pass. All right, and if the Monte Carlo simulation, just keep doing like sample pass and divide the number of crashes by the total number of pass. That gives you like a crash rate of an episode, and then you can convert that into crash rate per million miles or so, right? So, but of course, you can do that, but it's going to be really tedious. So first, you're going to have m episodes, and let's say if you have n is the number of states is humongously large. You know, think about the different geometries, different vehicle combinations. It's super large. And also, m is, if you add an exponent, make it exponential, it's extremely large. So there is a same curse of dimensionality. I mean, UMich's group discussed this before. That's a problem. And also, if you start from S0, you're mostly wandering between the safe states. It's hard to get to like near crash or even crash states. You're not going to have many crash states. So there is a curse of rarity. These events are rare. It's hard to get to there. All right. So if you just use the Monte Carlo simulation or field test, you're going to do 10 to the power of 10 AV calls or AV steps. What does that mean? It doesn't make any sense. It means you need to run a vehicle non-stoply for 30 plus years. It's not like you use it for 30 plus years. It's going to be run 24/7. All right, for 30-some years. All right. Even if you have all these fantastic behavior models, whatever, it's not an easy job. So with innovation from the UMH colleagues, they actually proposed the innovative important sampling approach to expedite this process. So what is the idea? Their idea. So for a general state, all right, you may have different transition probabilities. Normally, transition probability to a safer state is bigger, and transition probability to an adversary state is small, right? It's smaller. But their proposition is just to skew the probability to make this state more likely to transit to a danger state or crash state. And then these sample paths will have more likelihood to hit near crash or crash states. And with this innovation, you're going to explore more episodes that has high adversity measures. You're going to hit crash more often. And with that, you can adjust back that to the original crash rate based on important sampling methodology. And that can reduce the testing time to 10 to the 7th AV calls, which is 10 days, 30 years to 10 days. A lot of improvement, right? Thanks to their work. So we're still not satisfied. Feel like you have 200 models and different trees and different versions. You multiply that by these numbers of this. This is still going to be a big number, all right? Maybe it's not something that academic institutions can exercise. We want to further improve it. So what's our idea? All right, build upon their success. Where we're thinking, okay, one place where we can improve is you don't have to always start from S0. Because if you're starting from S0, you're exploring these safe states, which are not very useful to estimate the probability in this area. So instead, we can let them to sample from anywhere. All right, and instead of exploring n of steps in one episode, we can just estimate one step. So in this way, you're going to get to these non-rare states directly, and that's going to largely reduce the number of episodes from n to the power of m to n to the power of 2. So that solves the curse of rarity. And then you actually still there are so many different states. All right, think about all possible traffic scenes that you observed while you're driving. There are so many different states. So instead of dealing them together, the nice thing about this adversity-based Markov-Chain graph is you can actually group the states with similar adversity levels to the same beings. All right? And with this, you only need to deal with a very small number of aggregating Markov-Chain states. Look, maybe 10 or more, 20, that's enough. Think about the different adversity levels. Just on the order of 10, you only need to deal with them. And then this reduces a much smaller Markov chain. You have 20 states, 10 states, and you need to solve the transition probability of them. That brings the individual vehicle's behavior to the aggregated, like adversity transition behavior. The adversity transition behaviors are determined by AV and A-tree behaviors. But how do we find this out? If this can be solved, it's going to solve the curse of dimensionality. It's going to reduce the very high dimensional problem to one-dimensional problem with different beings. It's actually not that difficult. So what we're going to do is we're looking into the weighted sum of transition probability between all states in the bars. How do we solve it? We just do the sample. So you sample some states here, and then you just, for each state, you're going to sample the states from transit to other states. And you do a few samples, you average them out, you get the transition probability from this states, from this bar to the neighboring bars. And here the transition probabilities calculated transition probability is actually dominated by behavior models, HV or AV, and you can use the power law kind of similar models to do that. And you keep doing this, and you're going to aggregate them and solve that problem. So here's our solution. So we did the test, all right. Monte Carlo, again, is like 30 plus years, right? Actually, the state-of-the-art method is 10 plus days. And with our proposed method, it cuts it down by about 2 orders of magnitude, brings it to 6 hours. All right, and we looked into its convergency. You know, our results are pretty stable. This is our results. This is actually the red curve is the Monte Carlo simulation. Monte Carlo simulation doesn't converge until many rounds, but our results converges very fast. Right. So yeah, that's we're still working on this and try to hope to increase it. To improve it. And also, with this method, you can get a very good distribution of the near, collision distribution and near-miss distributions, like the Monte Carlo baseline and the proposed method, they match each other very well. And also, you can match the different types of collisions, side swipe, rear end angle, all these actually you can match them very well. So that means our estimation does not introduce any bias. It only accelerates the test. All right. So again, I just want to say this study is just starting this. I just scratched the surface. Actually, there is a lot more. Think about we're just looking into very simple geometry. All right. You can think about different geometries, runabout, intersection, interchanges. All right, and different geometries. And also, we just tested with limited data, right? And most of them are trajectories. And I think in the next few years, people will have more sensor data, end-to-end models are there, right? You're going to need to have richer data. So there is plenty of opportunities for us to collaborate together and collect all these data and try to develop models and evaluation methods. All right, so I just want to say what is our effort based on our resources. So our lab has 3 of this kind of vehicles. 2 are like this. Third is like a van. It's bigger. So, they can drive around and collect the data. And also we can, remove these sensor racks and put them to production automated vehicles and rent a Tesla, or actually using my own Tesla. Put them on there and do some data collections. And we also have a lot of other gadgets for students to play with, like signals and drones and robots. They're not in this study, but just to look into the generalization of some of these models. And with that, we can collect this kind of high fidelity data. You can merge the actual vision and the LiDAR and put it into the bird eye view and doing like segmentation, all these things. Then you're going to get a lot more richer scenarios, states, compared to like, every vehicle is got, right? And you can even get to the pavement conditions. So you can mainly make that state a lot bigger. All right, that's actually a direction. We're working on cooperative perception to have fuse vehicles, sensors of multiple vehicles, and we have an upcoming state project about estimating the winter performance of automated vehicles. We're going to put these kind of sensor racks and drive them around and see how these production vehicles, as well as our lab vehicles, perform in this inclement weather. And also another dimension to look into is as scenarios get complicated, your understanding needs to be, more intelligent. All right. So there is a rising space of research called spatial intelligence, right? That combines the foundation models, large language models, vision language models. And we have done some work, like we used it for autonomous driving. And we also try to do something not just for autonomous driving, but also inspecting like environment, like work zone inspections, MUTCD inspections. On the one hand, you have a guidebook, MUTC work zone field menu. If it's pedestrian path, you have ADA, federal requirements. You can use language model, vision language model to get the knowledge out of it. And also, on the other hand, we have like sensors. Could be from our vehicles, or could be from drones, or could be from anywhere sensor providers. And you're going to use some kind of like spatial intelligence AI to understand not only single object, identify single object, but also their relationships, their semantics. Right? That's actually probably Dr. Fifi Lee came here and give you a talk. She probably mentioned spatial intelligence, like cognitive map, all these things. You can basically extract them all in graph structures and compare all these graphs and trying to come up with a common language between physics and cyber, and doing some of the research. And that can be also used for scenario construction for AVS evaluations, all these things. So this is a really vast and new era of research that we can move to. Compared to, as we have more sensor data, as we have more ways of measuring, because we've been working on like aggregating the sensor data for quite a while, and then we also worked on at most trajectory data every vehicle is a dot, and you don't look into the environment and other things. But now you have different weathers, different signs, all these things. We need to move to next step to get actually get more data, and we want to bring our field to the next phase of working on this kind of sensor level data. All right, I want to say we hope we can start to work on this big collaborative initiative. Like this, rural autonomous vehicles for people. I mean, this work cannot be done by an individual lab, and like this is one of the projects that we collaborate with many institutes and companies. These are autonomous vehicle companies. Some of them are very nicely and agree to share their data and even use their API in this project. And UW Professor Wang is actually part of the team, and we hope to work with everyone to get some of the data to do the evaluation for rural settings. This is one of the examples, but there are other opportunities where everybody can attend. Like I want to say, we started this, but I never want to attribute the credit to just us. If you look into the OpenPA, this is it just as a frame. Okay, we haven't got a lot of data and going on, but the direction and the vision is along that thoughts. Actually, some of these are. So we actually worked with the multiple institutions, and we put they contribute data. We're going to put them in accreditation. I hope this is going to be put as a community effort instead of some labs effort. Think about like 15 years ago, 16 years ago, like computer science put the ImageNet together, and that boosted the field. And we really need to work on the benchmark and data, set up something that we have a common language to communicate, we have common metrics to work on, we have common data to compare against. And this is the effort that we start. And in order to work well with this kind of effort, we want to work broadly with different societies. For example, AACE, with support from actually Professor Wang, again, under his leadership of Center for Technical Advancement, we started the Smart Infrastructure Task Force. And some of these can go to this agenda. And also IEEE ITS as society. And has some of the technical committees that focus on testing. And these are just examples, and I really want to invite all of you guys to think about how we can extend this kind of collaboration and really set up grab these new opportunities. Yeah, that's my presentation. I want to stop here and open to any question if I'm not running over the time.
Thank you very much. Now let's open for questions. Anybody have any questions? We can use this microphone because we do have the webinar portion. Any questions? Maybe I can start a question. I think you try to find what's the distribution, right, at the end. But, for traffic crashes, human factor plays a major role. And a lot of cases, right, different kind of drivers, their behavior is so different. Like very senior drivers, they may need a lot longer time to perceive and react, while the younger person takes shorter time. Do you consider this could be addressed by one distribution, or they have to be initially two different distributions?
Yeah, so, yeah, that problem, that's a very good question actually, is whether one distribution here is enough or multiple distribution. Of course, if you have data, if you have more distribution patterns, that's going to be good because you can feed that into different areas with different demographic areas. But before that, you can start with one distribution. That is all lump all this population together. You know, you can have an average driver. Maybe these are old drivers and these are like young drivers, but you sort of superpose these two distributions that can still start your analysis. But as you get more data, and you know, it's just like when I said extending the state from a single dot to the vehicles, and it's the same way to the road users, right? You have different demographics and different cultures, and you can also just add the state to space longer and try to think about multimodal distribution or multidimensional distribution. Yeah.
Thank you, Sean. Relevant to this, right? In different driving scenarios, like you drive on like a clear dry pavement versus driving on icy surface of the road, I think that's also fundamentally different.
Right.
Do you think that also be described by the same distribution, or you need to be a
Right.
different distribution?
They're definitely different, and I said, if you just want to look into the average performance, you can do an aggregated distribution that includes a portion of that. Just let's say in Wisconsin, if we have 3 months of snow days and 9 months of non-snow days, all right, I hope that's I'm actually thinking optimistically. If that's the case this year, I'll be very happy. Then you're going to put 1/4 of the data in the winter distribution and 3/4 of the data in other dry pavement distribution. Superpose them together. That gives you a overall range. And if you do an average measure, that's going to be an average measure in Wisconsin for all year around. But that's not the best solution. If you can separate them, that's going to be great. We actually did an analysis with telematics data. So those vehicles, send out their speed acceleration data every couple of seconds, and you get 5% of penetration rate along all these roads, most of the roads. Look into the speed distributions and acceleration distributions. We found that in actually dry day, acceleration is like this, and in snow day, it's going to be acceleration means here. And actually, the people drive a lot more cautiously in the snow days. The acceleration extreme is much tempered. So for specific analysis, it's just like the more information you have, the more detailed prediction you can have. If you only have aggregated data, you can predict what's happening on average for a year. If you have more separated, segmented data, you can tell, okay, what's the performance of this vehicle in snowy Madison day in a neighborhood where aged people ride a lot, right? If you have that kind of data, and also that applies to all the different geometries, different pavement patterns. If you have that kind of data, you can answer this question as well. Yeah.
Yeah, thank you for the talk. I was curious also, it seems like this model was developed between vehicle-to-vehicle interactions, and do you think there's also the potential, I know it increases the complexity, but can you expand it to model for vehicle-pedestrian or vehicle-bicycle interactions? And you may have talked about that, I had to run out in the middle, so I don't know if I missed something, but I was just curious if you can also accommodate that, or, because I know the model parameters would be different.
Right, good question. You actually didn't miss much. I mentioned that, but it hasn't been done. So far, I just said there are so many open questions for people to address. Like, here is a framework. I actually think about propose this to be an open PID framework. You're going to have all these data all together, and then you can train a model. VRU would be, one more road user would be that category of behaviors. It's like just I don't have a lot of data, but if you guys test with your ADAS vehicle or if you work with Waymo, and probably Waymo is not going to let you to put sensors to measure their behavior. But anyway, if you can put some of the cameras and LiDAR around the vehicles, you collect the VRU interactions, you can get there. But that's a different type of modeling, and we can come up with a different scaling law, maybe, or different distribution.
Yeah, the predictive behavior is definitely very different.
Yeah.
Any other questions?
Thank you, Professor, for your insightful presentation. So I have two questions. First, I'm also very interested about scaling your part. So you did a lot of experiments and showed that the crash rate is now very close to real world. And I wonder if you also investigate like the distribution of severity of the crashes.
Yeah, here it is.
Is that although also very close to the real world?
Yeah, we compared with Monte Carlo simulation actually. Here, we haven't, we meant to add more information. Right now, in that study, I think we only had like longitudinal error and lateral error. And, I can, because, it really takes a long time in simulation to get the under run truth. We only got like, 27 crashes, which may not be sufficient to get all the distribution. But as we get more data kicking, we may get a bit more understanding of the distribution, whether that the severity level is matches. But right now, we don't have as good data about, you have to be in this kind of geometry and, this kind of vehicle, and we don't have that kind of data. But without that, I think this is fairly good prediction. But you're right, if we have, this is something we need to verify over the years, whether as we build more and more data, you can run more and more simulation based on this kind of scaling. We'll see whether they can extrapolate them very well.
Yeah, thank you. So my second question is that, so the scaling law is only applied for car following behavior, or it can also be applied to like lane changing?
Yeah, you see, they have lane changing. Otherwise, they're not going to be able to predict the lateral cutting collision.
But the model here is only applied to car following
No,
behavior?
lateral and longitudinal.
Okay.
All right. So both are fine, but they have different parameters. All right.
Thank you.
Yeah, sure. Yes, Mohammed.
Thank you, Professor, for this excellent talk. I just have two questions as well. First one is, so now you can predict like the crash rate, which is very equivalent to the real world scenario. So my question is, what is the application of this one? Like, why do you need this one?
Answer the fundamental question. If you get a Tesla, you want to know what is that. If you want to put it to FSD, what is the crash rate compared to human drivers? Is that useful for you? If you want, is that going to be? If you want to buy a Tesla, is that a useful information? Yes. Aside from what Tesla brags, you want to get third source. And also, as let's say, washed-up, let's say, washed-up, we're both W-dot. Like, they want to know how these vehicles behave in different environments. In some geometries, maybe their crash rate are particularly higher. And then if you can use this to predict it, then you can say, okay, before these predictions happen, before the crash happens, you know the problem, you can proactively solve it. So it's going to change the paradigm of reactive safety measures to proactive safety measures. You know why safety studies are always like reactive? Because we're using post-crash analysis. We learn from crashes. But now, if you have models, you can learn from modeling without the painful cost of collisions. All right. So that's actually another use. Of course, industry can use it. Try to get these laws. Industry, I talked to these companies, multiple companies, like Waymo Momentum, Waymo Mobility, and they're struggling with simulation, actually. They can do simulation, but it's hard for them to put the, a lot of companies are doing replay, right? They can only do replay. That's not interactive. Okay, the replay, whether I can find, mimic that trajectory. That's actually like what the companies are doing. If you work at these AV companies, you know that. Some companies like Tesla, actually, the video I showed there, actually, I think there is I don't know, it's actually more of like a generated video based Is it here? Yeah, here. They're doing this kind of high fidelity simulation, but it's a closed, it's new, and I don't know whether these vehicles just behave very well. It's just maybe slight modification of what you recorded in the real world. They said this is generated AI, we get it. But then if they know this kind of pattern, they can just embed those kind of behaviors into their simulators. That's actually very highly demanded by company. Actually, I don't tell you, but some of these studies were indeed used by the company. Some of my students told me actually, don't spell out the company. They're using this kind of behavior models.
Thank you. One more.
Yeah.
Researchers are doing autonomous vehicle research for many years now.
Mm-hmm.
Like they're trying to push the state of the art to the higher level. So my question is, even though people are researching for many, like all around the world, why we don't have fully autonomous vehicle yet? Like what is the gap? Like what we should do?
Yeah, the gap is here. They don't understand the behaviors, right? If you know all this scenario, all right. So let me tell you from here. All right, let's say if you really have a word model that has all these scenarios, you can navigate yourself on this side, avoid collisions. All right, but sometimes, it's not your problem, it's others' problem. You still can get into collisions. But even that, you don't really understand how it works. It's like the current training is, okay, I'm going to pick out some of the scenarios and let them run well in this scenarios, and then I think, okay, it's going to do well. Or really, with that kind of behavior translate to other scenarios. And there is also, I think another good thing about this is we really need to, people are saying corner cases, but how to quantify how corner the cases? Still, there is no quantitative measure, but you can come up with some kind of adversities, quantify them, and numericalize them into this kind of quantitative representation. If we do approach to this, I'm not saying we're going to reduce the crash to zero, but there is a huge potential for us to reduce the crashes. And autonomous vehicles are not many years. It's just like much younger than traffic flow theory. But traffic flow theory is like, I don't know, almost 100 years. But can we describe traffic behavior precisely? No, right? So we still have a lot of room.
Yeah, thank you.
All right, so you may still have more questions, but given the time constraint, so we have to stop our seminar and webinar here. But the good news is Professor Lee will be around for more time, because following this is our transportation mixer, right? So we also offer some pizza, and so you people can stay around, talk to our speaker, talk to each other. So I'm not sure if IT Washington has anybody here. But this is somebody will be here to officially kick off, their academic year and their connection to our students. Maybe we can wait for them to be here. But now I would like to represent, our Patron Center to show our appreciation to Professor Xiaopeng Li to travel for a very long distance, coming here to deliver the seminar. And here's our gift. It's actually a Patron mug and the local chocolate.
Oh, nice.
What is this? Okay.
All right.
Something. Like the ones before we had the same thing.
Yeah, sure.
Thank you so much.
Thank you so much.
Yeah.
Okay.
Now let's do a picture first. All right, so now let's give Professor Lee another round of big applause. Thank you. Okay, our autumn quarter regional transportation seminar is over. So now our transportation mixer.